Feel free to. Yeah. Okay.
Online questions or
Yeah, no rush. I'm used to things running.
Oh, yeah.
Bay Area time is always 5 minutes late, so.
Yeah. So in Europe, for example, when I've given colloquiums in European countries, they usually have .e or e.b. It's like 6 encoding or something else, which is basically, are you going to go start from the on time, or is it just going to be the next?
Oh, I see. That's helpful.
Yeah. Typically, they will tell you whether it can be a few minutes.
Yeah.
Those people can ask for anything. You have to ask all the audience the questions.
For master's students.
Oh, yeah, many PhD students actually. Like some from our lab, an entire contingent of their systems lab.
Okay, cool. I think this is probably the most well attended.
Oh, it should be a little bit better. And there's a bunch of people on Zoom. There's also a bunch of people on Zoom. Typically, the faculty who will be working on their prior potentially will be attending. Get started. Thank you everyone for attending Colloquium on this very nice and sunny day in City. But better to be indoors and listen to something exciting than be out in the rain, I guess. But it's my pleasure to introduce Mark Zhao from Stanford University, the other school in the area. Mark is a PhD candidate in electrical engineering at Stanford University, where he works with Chris Kozirakis on scalable machine learning. He's looking at GPUs and cloud computing. Mark has a very impressive resume, and the bio for this talk should have all his accomplishments. I will just highlight 2 of them. He won a Distinguished Paper Award at IEEE S&P, which is like really, really prestigious. And he also has his solutions being used by people at Meta, which, if you're in machine learning or anything of that sort, is a pinnacle of achievement. So with that, I will invite Mark and look forward to his talk.
Yeah, thank you so much. No, thank you so much for the warm introduction, and thank you all for coming here. I'm really excited to be here to share my work on building scalable systems for ML pipelines with all of you. Feel free to stop me if you have any questions. Just feel free to interrupt. Yeah. I think it is it? Is it not? Yeah, okay. Maybe I need to move it closer. No. But feel free to stop me if you have any questions, and I'll try to keep things generally on track. Cool. Okay, hopefully, yeah, thank you. So, all right, let's jump into it. So many of you have probably seen this figure or something like this before, right? And that's Probably because us systems folks love to use this image. So what this is showing is on the y-axis, the amount of compute needed to train these state-of-the-art machine learning models is rapidly growing over time, even outpacing trends like Moore's law. And we like to use this because we can kind of say that, okay, if we're able to build systems with faster GPUs or other accelerators or more GPUs, then that allows all of us to train larger, more capable, more complex models. Right? But I want you to take a second and think about what's missing here. And to give you hints, here's one word: data. So if we want to train increasingly larger models, we need increasingly larger data sets. And so these data sets are also growing rapidly, over 3 times per year. On top of this, we need all of this data faster. So companies like Google, Microsoft, Meta are buying millions of GPUs and deploying all of these GPUs in these data center scale training clusters with hundreds of thousands of GPUs. And if we want to actually use all these really expensive accelerators that we're buying, well, we need to process and ingest all of these data sets fast enough to feed the millions of GPUs consuming all of this data. So in summary, if we want to keep up with this growing data demand, well, real-world ML deployments require scalable data pipelines to manage all of this demand. And my key message today is really this: if we want to continue scaling all of our ML capabilities, training, deploying these larger, more complex models, we need to focus on collectively optimizing all of these different systems across the entire ML pipeline, not just only the GPUs themselves. And so to really illustrate this, let me start with an example of what a real-world ML deployment looks like using example of a recommendation system. And why recommendation systems? Well, if you've ever used apps like YouTube or Instagram or anything similar, you've interacted with a recommendation system. So these are used to suggest new and relevant content that's fit your interest. As a result of the scale of these applications, well, these systems under the hood need to handle massive amounts of scale. We're talking about billions of daily active users. And to continue improving the quality of these applications, well, these systems are also adopting all of the advanced techniques out there: generative models, agents, you name it. So let's take a closer look at what goes on under the hood of all of these applications. So let's start with the inference side of things, and let's assume a user, Ellie, is using an app like Instagram. And what Instagram does is calls this inference system under the hood, and this system is responsible for finding the best post to show Ellie. The tricky part here is that it needs to wade through billions of potential options of what to show Ellie, and it needs to do so within a matter of milliseconds to give us that response that we're used to. On top of this, as I mentioned before, these applications have enormous scale. So these systems also need to handle enormous scale, millions of current users. So what's actually deployed into production is not just a single system, not a single component, but instead we need this pipeline, this inference data pipeline that has multiple specialized data systems like feature stores, vector databases that work alongside all of these different accelerators running these specialized models like embedding models and deep neural networks. And all of these different components work together to collectively take these billions of options, find the best top few options in a matter of milliseconds. On top of this, we also need to continuously train and update the models that we're using inside these production pipelines. So we need a training system. And what this training system does is it takes these real-world interactions, Ellie liking a post, for example, and its goal is to train a better model that we deploy back into production. The tricky part here is that because of the scale of these models, the scale of these data sets, the scale of the amount of users that are interacting with these systems need to handle hundreds and hundreds of petabytes of data. On top of this, we're not just training a single machine learning job at once, we're running hundreds of concurrent training jobs doing things like hyperparameter search to find the best instance of a model to deploy back into production. And so to meet this computational demand from all of these training jobs, as I mentioned before, we're using these data center scale clusters, each with tens of thousands of GPUs that are ingesting an enormous bandwidth, enormous volume of data, upwards of tens of terabytes per second within a single cluster. So like with the inference pipeline, we need a training pipeline. And this training pipeline has multiple dedicated scalable systems that take this raw data, engineer it into actual data sets, store the data sets, and then for each training job, we need to further process these data sets throughout the lifetime of the training job, kind of on the fly, to generate these tensors, which are fed to the GPUs, which then, of course, train the final model that we deploy. So the point of me showing all of this is hopefully you see that real-world ML deployments require these complex data pipelines. And in this talk specifically, I'll focus on the ML training data pipeline. And I'll show you how we can build systems that can manage the massive and growing data demands of these modern real-world ML training jobs. And specifically, I'll show you how I've approached this problem in 3 steps. First, I'll talk about how do we build these scalable ML data systems to keep up with the growing storage and ingestion demands of these jobs. Then I'll talk about why we need to optimize the efficiency of these systems as well. And I'll walk through a few examples of optimizations that I've deployed in Meta's training fleet. And finally, I'll present a framework that allows us to make deploying these optimizations effortless, especially across a diverse set of ML training workloads and ML training pipelines. My research has also addressed other challenges throughout this entire ML lifecycle, which unfortunately I don't have time to discuss today. But to give you a high-level overview of some projects, I've built efficient tiered storage systems that are deployed at Meta, which are used to store these massive petabyte-scale ML datasets. Then once we've trained the models, I've worked on building inference frameworks that can take these models and use them to drive real-world applications like video analytics pipelines. And finally, I've built the hardware and software infrastructure that support these various pipelines, making sure that they're not only scalable, but also secure and resilient as well. Of course, happy to take questions on any of this, but for now, let me come back to this training data pipeline. And so let me start by going a bit deeper into how do we build and deploy these scalable ML data systems, especially for these recommendation models that I've been talking about. And this comes from my work published in ISCA. So let's come back to the high-level ML data pipeline. So at a high level, we take this raw data, for example, Ellie liking a post, James not liking a post, and this comes in as a continuous stream of just raw data, logs effectively. And the goal of the training data pipeline is to take this raw data and for each training job, continuously generate these tensors, which are understood by the GPUs, feed these tensors to the GPUs, which train the final model. So if you've ever trained a model, you might ask, why can't we do all of this locally, right? If you've ever used ImageNet, you might have downloaded ImageNet to your local storage, written PyTorch data loader that uses kind of the CPU on our local server to process this data, and then fed this data to your VM on EC2 or Google Cloud to train your actual model. And this setup doesn't work in production workloads simply because of scale. So what I'm showing here are 3 production recommendation datasets deployed at Meta. And you can see that these are tens of petabytes large, if not hundreds of petabytes by now. And so this size of data doesn't fit on local storage within our VMs. Yeah. I'll go over that in a bit, but for now, this is recommendation datasets. We can think of it as tabular datasets, so Hive tables and Parquet files, things like that. On top of this, when we ingest this data, the bandwidth needed by these GPUs is enormous. So what I'm showing here is a table in terms of the pre-processing demand of a typical 8 GPU training node. So these 8 GPUs need dozens of CPU sockets doing this continuous data pre-processing to make sure that they're sufficiently fed. So dozens of servers just doing data processing to feed these GPUs. And if we think of a typical maybe 2 or 4 socket, DGX machine, this just simply isn't enough resources. So the implications of not having sufficient upstream resources for storage or for pre-processing is that your expensive accelerators are just stalled waiting for data to come in. And that really cripples your training throughput, underutilizes your expensive GPUs. So one way that we can address this is, as I mentioned before, rely on dedicated, distributed, scalable systems throughout this entire data pipeline. So for example, at Meta, we take this continuous stream of raw data and we run offline data engineering jobs on them. For example, Spark jobs to take the raw data and engineer it into actual data sets. These are the Hive tables that I mentioned before. And then, so these data sets are then stored in this distributed and scalable file system called Tectonic Shift, which we, as I mentioned before, built to manage this hundreds of petabytes of data. And this is presented in my ETC paper. And then to keep up with the data volume, the data bandwidth demands of each training job, we actually built and deployed a distributed pre-processing service called DPP, which is presented in this ISCA paper. And the goal of DPP is to continuously process and ingest this data fast enough to keep up with the training demands of your GPU to sufficiently feed the GPUs, which of course train the actual model. So the point of doing this aggregation, right, taking these individual components, storage, pre-processing, and breaking them off into services, is that we're able to scale them to meet the demands of the GPU. So if we have some GPUs that need some bandwidth of data to keep fed, well, we can take our data pre-processing tier and scale it out, meaning allocate more resources into it to ensure that we can keep up with the throughput demands. On top of this, we can take our storage tier, allocate more resources to it to not only store the data sets, but also have enough IOPS to feed the rest of this pipeline. So this aggregation is effective at eliminating these data stalls, which may underutilize all of our expensive accelerators. But doing this comes with enormous cost. So what I'm showing here is a graph of the three recommendation models at Meta that I talked about, and a breakdown of the infrastructure resource capacity in Meta's data centers needed to support these models, broken up across storage, pre-processing, and training in red. So the takeaway here is that your data systems, your storage and pre-processing systems, can take up more capacity in these data centers than the actual GPUs, the actual accelerators themselves. And as I mentioned in the beginning, this data demand, volume, throughput is growing rapidly year over year. So the point I want to make here is that if we want to continue building these scalable ML systems, these ML data pipelines, that requires also improving the efficiency of not just the GPUs, but all the other components, storage, pre-processing within the end-to-end ML pipeline. So next, let me talk about how we can optimize the efficiency of these data systems. But before that, any quick questions? Yeah. So you can think of it effectively as an evolution of HDFS. So Tectonic is kind of the historic evolution of HDFS that's deployed at Meta. Shift is this kind of cache tier that we deployed on top of Tectonic to make it more amenable for the high I/O demands of training jobs. But it's your append-only distributed file system. You can think of it like that. Yeah.
The data center, you may have storage nodes separate from the compute nodes.
Yep, we do. Yeah, so I'll talk about that in a bit, but yeah, everything is kind of disaggregated. We have storage nodes, we have compute nodes, we have GPU training nodes. All of that needs to communicate over the network. And so network efficiency is a real problem. All right, yeah.
So you get the time synchronization. The GPU want to keep stopping the GPU. Everything needs to get time. Or else if you get too fast and your GPUs, you might back up the data. Right?
Yeah, so I'll talk a bit about this at the end. In terms of time synchronization, we can think of this ML pre-processing as asynchronous, where we're just trying to fill up a buffer, and the GPUs are continuously reading from this buffer. What we don't want to happen is that this buffer is empty, right? So as long as we kind of keep that buffer full-ish, then we don't need to worry about like cycle by cycle kind of, or iteration by iteration synchronization. Okay, so let's talk about some efficiency here. So to start, you may have heard of this term called Gestalt before, and typically it's used in design. And all it means is that the whole is greater than the sum of the parts, right? So my approach in building these efficient systems is what I like to call Gestalt optimization. And the idea here is that we can build individual systems optimizations throughout this entire pipeline that work together, that synergize together to enable greater optimizations end to end throughout this entire pipeline. And so to illustrate this, let me walk through two quick examples. And the first one comes from this ISCA paper. So we can think of this approach in 3 steps, where the first step is to really understand these applications well. And so, as I mentioned before, these applications are tabular data sets. So the recommendation data sets are these tables with many rows and columns. And specifically, there's this one column that's massive. And this is a features column where for each row, it stores tens of thousands of these features in a map that correspond to each user's interests. For example, Alice's last and like post can be stored as this list of integers. Because we have billions of users, we have billions of samples. So these data sets are massive. So once we have an understanding of what this looks like, the next step here is to really understand how the workload, how the ML training jobs use this data set and what that means for our underlying system. And so to skip a bit ahead here, the insight that we can get from looking at how all of these different ML training jobs read data is that each job typically reads only a subset of features. So what each job will do is it'll scan row by row this entire massive data set, but for each row, it'll selectively read out a certain number of keys from this features column, right? Might need features A, feature D, but not the rest. On top of this, collectively across these different training jobs, they tend to favor certain features over others. So what that means for our system is that, well, if we take a look at our storage tier, we see this very hot subset or very hot distribution of data, where the majority of our storage IOPS come from a minority, about 40% of actual bytes on disk. So there's this very hot set of data. So that's our system insight. Step 3 is, okay, let's take that insight and leverage it across these optimizations to improve efficiency. So let's specifically take a look at this interaction between the storage tier and this distributed pre-processing tier that runs for each training job. And typically how we store these tabular data sets is within these columnar files, for example, Apache Parquet or Orc you might have heard of. And within these files, how these files typically store these this features column, these keys and values, is it kind of intersperses all of the different keys and values for all these different features together. And so what this means is that when a training job wants to read certain features, for example, A and D, this pre-processing worker has to read the entire kind of batch of rows from disk, reconstruct those rows in memory, and then for the features that the training job doesn't need, for example, B, C, and E, it'll simply just drop that data and pass only the features that it cares about and the values for those features onward to the GPU and to pre-processing. So this wastes a lot of systems resources spent reading this unnecessary data and then just dropping it after kind of doing all this work. So the first technique that we can apply to really address this problem is this idea of feature flattening, where we'll go inside this distributed storage tier and kind of modify how the files are laid out a bit. So we'll add a bit of metadata to these columnar files, and we'll kind of rearrange how the bytes are laid out such that the feature values for each of these feature keys across the rows are laid out as a contiguous byte stream on disk. So all the values for feature A are kind of laid out together. And now what this allows us to do is when we want to read certain features, we can do so with very precise seek operations where we don't overread any data. So this is great because we are able to avoid all of this overhead, right? So that improves pre-processing throughput because each of these workers has to do less work for each batch. The downside is that this file system runs on hard drives, and adding more seeks to hard drives is horrible. So this extra seek overhead cripples storage throughput by almost 97%. Okay, so let's try to address this next problem. And here we'll go into this pre-processing tier and apply this idea of merging reads. And so this idea is pretty straightforward. If there's features that we want, A and D, and there's kind of data in between them, let's just go ahead and read all of this data as in one seek, including the data that's in between the features that we want to read. And so this is great because it eliminates these seek overheads, but you're obviously thinking, okay, we're kind of back to square one, right? Where we're overreading data and then we're just dropping it. So what's really the point of doing this? If you bear with me for one more technique, let's go into this feature engineering layer, these Spark jobs or ETL jobs, and let's add this idea of feature reordering. So the insight here is that we can actually run data analysis jobs that understand what features ML training workloads like to read together. So for example, let's suppose that we understand that all of these different ML jobs like to read features A and D together. So when we actually generate the data, when we write these data sets, let's just go ahead and reorder how they're laid out so that A and D are right next to each other. And now when we read the data for these pre-processing workers, we can get exactly the data that we want in as few seeks as possible. And so hopefully you've seen this idea here where our initial problem was tackling this idea of improving the overall efficiency of the distributed storage and this pre-processing tier. The key insight is this idea of synergy, where each of these optimizations aren't necessarily effective by themselves, but working together, they kind of synergize together and enable this greater efficiency across the end-to-end pipeline. And specifically, we're able to deploy these to improve storage efficiency by 84%, pre-processing efficiency by almost 2x. And finally, I've implemented and employed these optimizations into production across Meta's training fleet, which translates these efficiency benefits on paper to actual real-world impact. And so next, I want to talk through another example to really drill in this idea of kind of end-to-end optimization. But quickly, I want to ask if there's any, yeah.
Caching, but I didn't see any caching going there.
Yeah, so caching is definitely one part of that. I'll talk a bit about that at the end. There's various forms of caching that we can deploy. There is data reuse across training jobs. And so that's what the tectonic shift work is trying to address, is to put kind of features that are reused across training jobs in a really high IOPS, highly IO efficient flash cache tier. There's also other forms of caching, like for each training job, you'll reread the same data over multiple epochs. And so at the last part of the talk, I'll talk about how we can automatically kind of insert different cache operators to address that case. So caching is definitely in play here. Yep.
I think selecting those features is not a trivial task, right? So for each and every user, out of those 1,000 features,
Yeah. Yep. Yep.
I'm assuming that there's also another learning model as such, which is going to find out all these things and then say that, hey, these are the features that are going to be selected.
Yeah. So that's feature engineering or feature selection. That is a very active area of research on how do you pick the right features for the job. So here we assume that the ML engineers tell us what features that they want to do. So we're not selecting the features on their behalf. They tell us that, hey, I want to read features A and D, and we'll optimize the system under the hood to make reading those features more efficient. Yeah, we're assuming that, but that's in terms of kind of really cool, interesting research opportunities, combining all of this I'm hitting on the right point here. Cool. So let me quickly go through another example here, and this comes from my work in MLSys in 2023. And so step one is, okay, let's understand the application, right? But what I didn't show you last time is that these data sets look more like this, where each user simply has multiple samples associated with that user. And this is because every time a user requests an inference, for example, views a post on Instagram, we generate a training sample that kind of corresponds to their interaction with that specific recommendation. But there's a phenomenon in these recommendation systems, which is the values inside this features column are only updated for each interaction. For example, Alice liking a post. So if Alice doesn't like a new post in between her views of different posts, well, the values here don't change at all across these different training samples. And that directly leads us to our system insight, which is that there's a massive amount of data duplication in these kind of features here within these recommendation data sets, where almost 80 to 90% of bytes in Meta's recommendation data sets correspond to these duplicate feature values across rows for a given user. And of course, this causes a massive amount of overheads in terms of storage, pre-processing, training, just spent operating on redundant data, right? The same data over and over again throughout the entire pipeline. So it would be great if we could better encode or maybe deduplicate these samples to eliminate these overheads. The tricky part here is that these duplicate samples are typically spread across billions of other samples from billions of other users. So if we want to, for example, come up with a new GPU kernel that does this better deduplication or better encoding? Well, the GPU only sees a small mini batch of data at a time. And in this small window of the entire data set, there's typically not much duplication and not much that you can do in this isolated system. So that leads us to the fact that we have to do this end-to-end kind of co-design here. So here, let's start with the upstream part, this data engineering layer, and we'll add this technique of just clustering all of these duplicates together. So every time we generate one of these training table partitions, let's just go ahead and run a clustering job that groups together all of the samples for a given user together within this data set. For example, all of Alice's samples will now be kind of coalesced together in this data set. And this leads us to two immediate systems benefits. First, because these columnar files are compressed, by grouping together all of these duplicate samples, we get much better compressibility and much better storage efficiency just from kind of native black box compression techniques like Z-standard. On top of this, when these workers read the data over the network, it's still compressed, better compressibility, fewer bytes over the network, and better kind of I/O efficiency from our storage tier and our pre-processing layer. But the real benefit here is this idea of synergy, where by grouping together these duplicates, that enables downstream components to really leverage this idea of deduplication to do more. It improves their capacity to do more efficient deduplication. So to really capitalize on this much higher kind of duplication within these smaller batches, we have to address this next problem, which is that these tensors that the GPUs operate on are not natively compressed and still have a lot of duplication. So here, let's come up with a new tensor encoding that we generate in the pre-processing layer to efficiently encode all of these duplicates. So typically in PyTorch or in TensorFlow, to represent these sparse features, like kind of these tabular data sets, we use a tensor called a key jacket tensor. So the pre-processing worker will read this batch of data from storage, and it will convert it into this tensor, which has two lists, a values list and an offsets list. And so for each row in this batch, we'll have an entry in the offsets list for that row, which stores the offset in this values list, which encodes the row's initial values, 3, 4, 5, as you can see here. And then we'll send this tensor for more pre-processing and to train on the GPUs. The issue here is that because the GPUs don't know that this data is kind of replicated over and over again, right? They're just spinning cycles doing the exact same work on all of these values, even though they're similar across these different rows. So that causes a lot of GPU overheads. So to really, the first step in addressing this problem is, okay, let's come up with this new tensor encoding. And here we introduce this inverse lookup tensor, where list, which has an entry for each row in this batch. And that entry will point to the offset for that row, which will encode the values as before. And so the key here is that by adding this additional layer of indirection, we're able to significantly better encode all of these duplicate values before, as opposed to repeating, for example, 3, 4, 5 over and over and over again. And this, again, leads us to this idea of synergy, where now we're able to leverage the GPU to avoid having to have it repeat work over and over again. So the last part that we need to do in this pipeline is, well, let's make the GPU, the model architecture actually aware of this new tensor encoding. Right, so here we deploy this technique called encoding-aware training, but the high-level idea here is that we can go into the model architecture and into all of these different PyTorch modules that we use to build up this deep neural network. And each of these modules we can effectively replace with a plug-and-play version of a module that does the same thing, but it understands how to work with these inverse key jacket tensors. And the high-level benefit here is that because these tensors have fewer values that these modules need to process, the GPUs, again, just do less work. For example, when we send data over the network for kind of this data parallel training or model parallel training, there's fewer bytes in these sensors, fewer network requirements. We perform embedding lookups, like, for example, same with LLMs on these tensors. And because we have fewer values, we need less memory requirements to store and to read these embeddings. And finally, we perform compute over these embeddings, pulling them together And again, fewer values, less compute required. So in summary here, I've talked about how we can leverage the characteristics of the data itself, what the data looks like, to drive these various systems efficiency optimizations, in this case, deduplication. And the key insight here was, again, this idea of synergistic optimizations across the end-to-end pipeline. And by doing these optimizations, we're able to improve training throughput by 2.5 times, pre-processing efficiency by 1.8 times, and storage efficiency by up to 3.7 times. And like with the ISCA work, we've also implemented and deployed these mechanisms into production across Meta's training fleet. So I want to pause here and see if there's any quick question. Yeah.
Is there any concern about the fact that the batches?
Yeah. Yeah, no, that's a great question. So in terms of the semantics for the model itself, we don't change what the model sees, right? So if there's a lot of duplicates in a batch, we'll make sure that the model still sees the same number of samples. What we are changing is the ordering at which the model sees those samples. So for example, all of Alice's samples used to be seen across different mini batches in the data set, and now they're seen within maybe a smaller number of mini batches. And that's a really great point with a lot of interesting analysis behind it. But the high level summary is that at least in the workloads that we've looked at in Meta's training workloads, doing this reordering is kind of ISO accurate or improves accuracy a tiny bit. So it doesn't affect how the model learns that much, or it improves it a little bit. And the insight behind that is for really rare kind of feature values, this really long tail feature values, by grouping all of them together inside the same mini batch, that the model sees all of these rare values a fewer number of times. So that helps prevent the model from overfitting to these rare values. There is probably a lot more, we can definitely do a lot more analysis here, and there is work in the ML space to understand this a bit better, but from empirical evidence, that's what we see. Cool. So hopefully you've seen just how impactful all of these various optimizations are, but maybe at the same time, you've seen that applying them takes a lot of manual effort, reasoning about the characteristics of the data set, instrumenting all these various components. So instead of going through another optimization example, let's see how we can automatically apply these efficiency optimizations across the pipeline, especially across diverse ML workloads. And this work called Cedar will appear in VLDB later this year. So one option if we want to process a lot of data is to use traditional data engines like Spark or Beam or Flink. And these engines are typically used within this ML pipeline, but normally for this offline data engineering kind of batch workload. But for this online, on-the-fly, kind of last-mile pre-processing component, we use other frameworks like PyTorch data loaders or TensorFlow data and similar frameworks. And this is because traditional data processing has very distinct requirements from ML pre-processing. So in traditional data processing, we really care about massive parallelism, very high throughput, using a massive amount of resources to answer a SQL query as fast as possible. And on top of this, we can program these workloads using a very structured interface like SQL. But for ML pre-processing, if you've ever written a PyTorch data loader, you'll know that these are very ad hoc, right? We're using 1,000-line Python files or even bash scripts that are calling third-party domain-specific libraries and operating on these very unstructured tensors. On top of this, as you'll see in a bit, there's a lot of unique optimizations that we can do specifically for this ML pre-processing pipeline that we need to leverage and take advantage of. And finally, in terms of resources, it's really about right-sizing our resources. It doesn't make sense to throw as much processing capacity as we have, because doing so doesn't improve your training throughput. What we want to do is we want to use just the right amount of resources to do this data processing to match the bandwidth demands of your GPU. So if we want to build an efficient general purpose framework to do all of this, to do ML pre-processing, what do we need to do? Well, we need to address all of these challenges. First, we need to provide users with a very easy to use programming interface that at the same time allows us to capture the semantics or the intent of what the user of what this pipeline wants to accomplish. And this is important because we also want to deploy these efficiency optimizations, but we need to make sure that these optimizations don't change the semantics or the output of this pipeline. And finally, as I mentioned before, it's about right sizing the amount of resources that we employ to meet the demands of your various diverse ML training jobs. So this is difficult to do because, well, these optimizations can introduce a lot of different complexities. So for example, if we have a very simple image pipeline here that takes an image and then blurs and crops that image, well, optimizing it introduces a ton of complexities. So for example, in this work, we introduced this notion of a semantic preserving reordering. And the idea here is that if we want a blurred and cropped image as the output of this pipeline, we can execute that in a number of different ways. One option is we can first blur the image and then crop it, or this is equivalent to first cropping the image and then blurring it. And having these choices is important because, well, the option on the right is much more compute efficient because we're performing this really expensive blur operator over a much smaller image. And so this is great in this case, but there's two problems here. One is, how do we know in general when these reorderings are allowed according to the semantics of the pipeline? So it works with blur and crop, but what about different black box operators or UDFs? And secondly, how does this interact with other optimizations that are out there? So one optimization that everyone knows is caching. And so one option that we can deploy here is we can take the output of the pipeline and cache it. And for each epoch or pass over the data set, we can just read from cache instead of recomputing the entire pipeline. But suppose that we know that this operator is a random crop operator. So what that means is that we actually can't cache the output of this because doing so would kind of nullify the randomness of this operator and impact your training. So what we can do instead is, okay, we can perform this expensive blur and then cache it. And then on the fly, every epoch, we can perform this random crop dynamically. And so you might see the complexities here where there's no one right solution, right? The left execution plan is more compute efficient, as we saw in the previous slide, but the right plan is more cacheable. So the plan that works best really depends on the specifics of your training job, the dynamics of these operators, what hardware you're running, and a lot of other factors. And to maybe complicate this a bit more, there's a lot of other optimizations that we can apply to this pipeline. For example, we can take each of these operators and run them on a different piece of hardware. We can use the training host CPU, we can use a distributed service like TPP, build a new accelerator for it, and anything that you can imagine. We can also take these operators and fuse them together to run at once, and so that eliminates some data transfer overheads between them. We can prefetch this pipeline so we can overlap its computation with your training job. The takeaway here is that combining all of these various techniques introduces this massive design space or search space that we have to look through. So to address this challenge, I built Cedar, which is this framework that allows users to define these end-to-end ML preprocessing pipelines. And the goal of Cedar is to take these pipelines and execute them such that we're able to meet the demands of your training job while also being really resource efficient, using as few resources to do this data processing as possible. To do this, Cedar has three main components. We have a composable API that allows users to build these pipelines. Then we'll take this pipeline and apply a series of static optimization passes over it to generate this really efficient execution plan. And this is before the training job starts. And then when the training job is running, we'll dynamically and continuously right-size the amount of resources that we deploy to meet the demands of your training job without over-provisioning resources unnecessarily. And so let me quickly walk through each of these components one by one. So Cedar has this high-level kind of declarative API, but I don't want to go into the details here, but what I do want to highlight is that we're able to have users provide very lightweight hints that allow Cedar to understand the semantics of the pipeline. So specifically, users are able to supply these dependency constraints between operators, kind of like partial orderings, that will constrain our ability to reorder certain operators when we do these optimizations. Users are also able to label which operators are random, which will prevent us from caching after them. So then we take this pipeline And offline, we run these static optimization passes over it. And so this proceeds in a number of steps. So first, we'll take a specific optimization technique, for example, reordering here, and we'll enumerate all of the possible ways that we can generate an execution plan by applying that specific optimization technique. So we'll reorder all the different operators here while ensuring that the plans that we generate are permissible. They don't violate the semantics that the user supplied to us. Then we'll use a series of cost models to estimate the cost of executing each one of these plans. For the high cost plans or the inefficient plans, we'll prune those away, we'll get rid of them. And for the efficient plans that are left over, we'll take those and we'll kind of recurse on this, where we'll iterate on this. We'll take another optimization technique like caching here, and we'll apply that technique, generate more plans, prune those plans away, et cetera, until at the end of the day, we're left with this really efficient, optimized plan that combines a lot of different optimization techniques together. And so at the end of this, we have this plan, and we're ready to start training. So we'll start by running our training job, deploying this plan, and the goal of this dynamic kind of runtime is to allocate the right size of resources to meet the demands of your job. And we'll do this effectively via back pressure, where we'll insert these buffers throughout the entire pipeline, and we'll use the lengths of these buffers, like I mentioned before, to make our resource scaling decisions. If there's very high bandwidth demands, we'll see small buffers, and we'll scale up our amount of resources deployed to increase the throughput of pre-processing. If there's low bandwidth demands, we'll scale down. And what Cedar is also able to do is, if we detect that it's beneficial, we're able to dynamically switch the execution engine that we use for pre-processing. For example, if we detect that it's possible to run everything just on the training node's host CPU, we're able to dynamically make that decision and only use that resource. And so to show you that all of these techniques combined allow us to meet this goal of meeting your training throughput demands using the least amount of resources, let me quickly walk through 2 quick results. So first, I'll show you how these static optimization techniques can really maximize the efficiency of these execution plans that Cedar uses. And then I'll show you how Cedar can take these optimized plans and then dynamically scale the amount of resources to meet the demands of your training job. So first, let's talk about these optimizations, static optimizations. So we compared Cedar against several state-of-the-art ML preprocessing frameworks, like your PyTorch data loaders, TensorFlow Data, FastFlow, et cetera. And for each of these systems, we gave these systems 2 different kind of deployment scenarios. First, we have a local scenario where each system only has access to the training node's host CPU, and it can only use that to perform preprocessing. We also have a remote scenario where additionally, these systems are able to offload some of the execution to a remote distributed service like DBP to scale out or increase the throughput of preprocessing. I'll show you more pipelines in a bit, but for each kind of domain of pipeline, for example, computer vision in this case, we built these pipelines using different ML frameworks like PyTorch and TensorFlow. And this is important because certain systems like TF Data aren't cross-compatible. Because TensorFlow Data uses TensorFlow under the hood, it's not able to support these PyTorch pipelines. And so, as you can see here, we ran these experiments across 8 different ML pipelines, from computer vision to NLP to speech. And each of these use different frameworks like PyTorch and TensorFlow. And the takeaway here is that Cedar is able to support all of these different ML pipelines and ML frameworks. And by combining all of these optimization techniques together, using these static optimization passes, we're able to improve the efficiency of execution by up to 1.9 to 10.7 times compared to these state-of-the-art baselines. So next, I want to talk about, okay, now we have this really efficient optimized plan. How can we right-size the resources deployed to it? So what I'm showing here is for the computer vision torch pipeline, Cedar decides to execute this plan by offloading some of its processing to a remote service. And the blue line shows that as we increase the parallelism, the number of processes allocated to that service, how does the throughput increase? Then we set 5 different throughput targets as represented as a horizontal red line. So you can imagine this specific horizontal red line as a training job that needs 600-ish samples per second to make sure that's fully fed, right? The GPUs aren't stalled waiting for data to come out. Then the vertical red line here that intersects with each of these horizontal red lines represents the auto-scaled parallelism that Cedar converges to for each of these different throughput targets. And so the takeaway here is that what we want to see and what we do see is that the intersection of these red lines is just below the blue line, because this means that Cedar is able to achieve a throughput that's just greater than the throughput target, but using as few resources as possible, right? This vertical red line is not all the way out here using a ton of distributed processes. And quickly, I want to highlight that for very low bandwidth scenarios, we don't use any distributed resources unnecessarily. And so to summarize this work, Cedar addresses this problem of automatically optimizing the efficiency of data preprocessing across these diverse ML pipelines. And specifically, Cedar provides users with a framework that combines a composable API, these static optimizations, and this dynamic runtime. And collectively, Cedar can use all these different components to meet the diverse training demands of a lot of these different training jobs with very high resource efficiency compared to current systems. I built Cedar from the ground up, and it's open source and highly extensible with the goal of really hoping to catalyze and drive a lot of future work in terms of ML data systems research. And that's what I want to spend a few minutes to talk about at the end in terms of what's next. But before that, any quick questions on my past work? Cool. So yeah, I want to take a few minutes to highlight what I think is really exciting going forward. And I think that there's still so many opportunities when we think about how do we build systems for the entire ML pipeline and the entire ML lifecycle across each of these areas: ML data systems, serving systems, and the underlying hardware and software infrastructure. And let me quickly highlight some opportunities in each of these areas. So first, I've talked a lot about building efficient data systems. And there's still a lot of opportunities here going forward. First, we really need to understand how to apply and integrate decades of traditional data systems research into this new domain of ML preprocessing and ML data pipelines. But at the same time, as you've seen from this talk, there's a lot of unique optimizations here, like this reordering that I was talking about, that exist for these ML data systems, and a lot of opportunities to explore new optimizations that can be uncovered here. And finally, I think that ML preprocessing is a really rich area where new hardware accelerators can really make an impact beyond our current focus of just really optimizing for these dense matrix multiplies that a lot of accelerators are focused on. I also think that building useful data systems is really important. And this is timely because we've seen this recent shift towards more data-centric machine learning, where data scientists and engineers are exploring algorithms like dataset selection, feature engineering, augmentations that don't change the model itself, but changes the data and how the model learns from the data. So the issue here is that I think that there's this gap in actually building real systems that both provide these data scientists and engineers with the right information and tools to explore these algorithms, but also allow them to extend and deploy these mechanisms once they've developed them into practice in a real-world scalable system. And I think Cedar is uniquely positioned as a platform to build and explore these ideas on top of. Secondly, on the inference front, we've seen a lot of recent focus on these generative applications. And specifically, these applications are increasingly using these compound systems with multiple interacting components, such as LLMs being deployed in a reasoning chain like chain of thought or tree of thought, using data retrieval from vector databases, using tools, agentic frameworks, et cetera. I plan to build frameworks that are able to serve these applications by collectively optimizing the end-to-end compound AI pipeline instead of focusing on just a single component. And this is similar to my approach with the training pipeline, but another reason why I think this approach is really promising is that my past work on Llama in SOCC built a serving framework for these video analytics pipelines, which also have multiple interacting components and video reasoning models. And the takeaway from that work was exactly the same, where instead of if we want to really maximize application performance, we need to focus on optimizing the end-to-end pipeline for these applications as opposed to being laser focused on maybe just a single component within this pipeline. And finally, I plan to build infrastructure that's not only scalable, but also secure. And this is especially important because recent work has shown that the interactions between different components in these compound pipelines can actually introduce new vulnerabilities that compromise data security and privacy. And to really address this, we as a community just need to first understand these interactions better. What is the attack surface? What vulnerabilities exist out there? And once we have a good understanding of these vulnerabilities, I plan to build hardware and software infrastructures that can better ensure data security and privacy end to end. And to do this, I'll first begin by formalizing the interactions between these various components and systems, and then deploying full stack hardware and software security solutions, like with my previous work on building accelerator enclaves throughout this entire pipeline to guarantee this end-to-end security. So I want to quickly just summarize what I've talked about in this talk, which boils down to 3 important points. First, if we take a look at real-world ML deployments, they're much more than just a bunch of accelerators. They're these complex pipelines with many diverse interacting components. And if we want to continue scaling our ML capabilities, we need to focus on building systems for all of these different components end to end. In this talk, I've shown you how my work achieves this by building scalable, efficient, and easy to use data systems that can manage the massive data demands of these modern training jobs. But going forward, I think that there's still so many exciting research opportunities to continue to improve ML systems from training to inference, from hardware to software across this entire stack. And all of this is possible when we start kind of thinking outside the confines of just GPUs themselves and instead look at the end-to-end pipeline. Thank you so much for your time, and any more questions I'm happy to take. Yeah.
Maybe the question, dynamic scaling, right? The one that you're doing for your server. So how does that come along? What is the cost function that you're using in order to scale these processes amongst the?
So I wouldn't say it's a cost function. We're effectively kind of just using back pressure, where what we want to guarantee is that if you take a look at the buffers inside this pipeline, we want to make sure that they're above some threshold, right? So we're kind of doing kind of hill climbing effectively to allocate more or less resources depending on how full these buffers are. You feel free to call. I didn't. Yeah.
So this is, I'll make it, or ask you to make a comparison, you might not be able to necessarily make it. But like, so if you read the Llama 3 stable of models paper, so Llama 3 was like a 52-day training on 10,000 H100s. Yep. It had about a 45–50% GPU utilization across that 52 days.
Yeah.
And then DeepSeek, they have their Fireflyer AI HPC thing, and they claim they're getting like 95% GPU utilization on worse export GPUs to internal US GPUs. And part of this is like, as best as I can tell, they're sitting there writing PTX code. Yeah. But then they have this 3FS file system that I haven't quite figured out what the magic of that is for that. But it looks like that was very specifically engineered for this one task. Right? Yeah. You're building more of a system that can be composed in different ways to use for a variety of different tasks.
Sure.
For that. What do you think? Like, do they get most of their value out of that specific system engineering? Yeah. Or just they have 100 engineers to throw at it? I don't know what. I mean,
I think that's part of it, right? Like if we build really bespoke solutions like DeepSeek, using a various combination of these techniques like floating point training and all writing like hand-coded PTX code, then yeah, you can definitely get all these efficiency improvements. And I think if we are in a scenario where we have one goal in mind, which is to train this really cheap model, then that works. And so maybe you've seen this from my earlier work where we have these recommendation systems, right? And we have these data sets that we want to, specifically improve the efficiency of how we store and manage these data sets. And so doing bespoke optimizations for those is great, and we've seen a lot of benefit. But I don't think just doing that is enough, either in the LLM case or in the data pipeline case. For example, in the data pipeline case, there's lots of other workloads out there other than recommendation systems. And so the last work that I talked about was how do we build a framework that can take inspiration from all of these optimizations and compose that into a full-fledged system that works in a general purpose case. I think for LLM systems, there's this trade-off, right? Which I think we do need more general purpose efficiency optimization. So you can't just take what DeepSeek deploys in their case and apply it into, you can't spin up a VM on Google Cloud and have all of their benefits work directly there. And so there are use cases where in a general purpose where we want this kind of flexibility and kind of fungibility of what techniques we employ. And so I think maybe to answer your question, doing these specific optimizations is half the step. The other half is, okay, how can we incorporate them into a framework that allows everyone to actually get the benefits here? Yeah. Okay. Okay, cool. Yeah.
ML pipeline, is it like a platform inside of Meta that other teams use, or do they create their own pipeline based on this pipeline?
So the last work, Cedar, I talked about, that's kind of external to Meta. That's an open source platform that we built at Stanford that anyone can use. In Meta, there are various similar kind of frameworks that people use, like FB Learner is a typical thing, but there's also open source equivalents like Airflow and these other kind of ML orchestration platforms.
I was
Hopefully.
wondering if teams would get mad at each other, like the retargeting team and the timeline generation team are like, we both need this.
Oh, for sure. I think that's a really big problem where, these individual teams don't have a view of this end-to-end pipeline. And so they're not able to do these kind of synergistic optimizations that you need to instrument in multiple areas across this pipeline. So for example, if you're an ML engineer, you don't necessarily have a view of like how you lay out your bytes on disk. And so I think what my research argues is that we do need this kind of crosstalk between all of these various components, from the model architecture to the file system and the file format, to really get this full benefit that we need in the real world. Yeah.
Sort of a combination.
Yeah. Yeah, that's where I think something like PL could really come into play here. And I'm not just saying that because you're a PL person, but like I'm being right. So I think there's various mechanisms that we can think about to really extract out this information. But at the end of the day, some of these constraints just boil down to the fact that users have this kind of intimate knowledge of, hey, these black box user-defined functions are reorderable or are not. And currently our solution is, okay, we have to capture that information somehow in our data flow algorithm. But if there's a way that users can express this in a more lightweight manner, that would be really valuable here. And these current hints that we have are very targeted to specific optimizations. But if we're able to capture maybe everything that we want about this entire pipeline and distill out other types of optimizations from this end-to-end pipeline, that's what I think is a really big opportunity here.
So we'll take a break and thanks. Mark is going to be here for the next minutes or so to grab feedback. So that's the time, Mark.
Yeah, thank you, everyone.